All right, here is a notion that for some reason confuses. But let's beat on it for a little while and we'll see what happens. All right, independence. The heuristic behind independence. Independence is a relationship between events. Two events are independent if learning that one of them happened doesn't tell you anything about whether the other happened. They're uninformative with respect to each other. Okay? So if I toss a coin twice in a fair way, the event that the first toss gives me heads is independent of the event that the second toss gives me heads. Knowing that I got heads on the first toss doesn't tell me anything at all about whether I got heads on the second toss. Does that make sense? It's uninformative. Right? It's different from being disjoint. Right? They're not disjoint. I could get heads on both tosses. You get heads on the first and on the second. Right? The heuristic for independence is knowing that one event happened doesn't tell you anything about whether the other did. The mathematical definition is, so how do you say learning that one happened doesn't tell you anything? How do you make that math? Well, you're saying the conditional probability of one event given the other is just what the original probability was of the first event. You didn't learn anything by learning that the second event happened. You didn't learn anything about the first. So probability of A given B is just the probability of A. Learning that B happened doesn't tell you anything about whether A happened. It doesn't change the probability. Similarly, probability of B given A is just the probability of B. Learning that A happened doesn't tell you anything about whether B happened. Now, the definition of conditional probability involves dividing by something that in some circumstances might be 0. And so we have to rule out the possibility that P of B is 0. We can come up with a definition of independence that doesn't require this by just saying we define two events to be independent if the chance of their intersection is the product of their probabilities. Now, that's equivalent to this unless P of A or P of B is 0. If P of A or P of B is 0, this definition still makes sense, but a definition in terms of conditional probability doesn't. So let's just do the math. Let's suppose that P of B isn't 0. So P of A given B is P of A intersect B over P of B, right? And we are saying that that is, in fact, equal to P of A if the events are independent, right? If the events are independent, learning that B happened doesn't tell me anything about whether A happened, so this conditional probability should be equal to this unconditional probability. That's our stopgap definition before we do something more general. Well, if that's true, I can multiply both sides by P of B, and that says that P of AB is P of A times P of B. Okay? This expression only makes sense if P of B is not 0. This expression always makes sense whether P of B is 0 or not. So we take this to be the definition because it's a little bit more general. Okay. If this holds, that holds, as long as you're allowed to divide by P of B.